We are now on the 6th chapter of Mechanics 107, and it is all about beam deflections. One of the most important application of beam deflection is we are now able to analyze statically indeterminate beams. So again, what is statically indeterminate beams? So as I have discussed before, these are the beams that cannot be solved using the three equations of equilibrium, which is the summation of forces horizontal, vertical, and the summation of moment. So there are several methods available for determining beam deflections. We have four methods. First one is the double integration method, in which dito tayo magfo-focus talaga sa video lecture na to. Next is the area moment method. We also have the conjugate beam method and the method of superposition. So this video lecture will mainly focus on the double integration method. So the common basis of these four methods is the differential equation that relates the deflection to the bending moment. They are based on the same principles, but they differ in techniques. Beams are frequently governed by rigidity rather than the strength. That's why building codes specify limits on deflections as well as the stresses. Excessive deflection of a beam is not only visually disturbing but may cause damage to other parts of the building. For this reason, the building codes limit the maximum deflection of a beam to about 1/316 of its length. So for the double integration method, the primary advantage of the double integration method is that it produces the equation for the deflection everywhere along the beams. So we have here a beam, for example, with a certain length, and then nagkaroon siya ng deflection. Ayan. So kumuha lang tayo ng small portion or a portion of the beam. So this is now the exaggerated deflected beam, or the exaggerated diagram that shows the deflected beam. So, nag-exaggerate lang natin yung deflection ng beam para makita nyo yung difference. The edge view of the neutral surface of this deflected beam is called the elastic curve. So, ito yung ating elastic curve. The view of the neutral surface of the deflected beam. So, actually, the deflection is very, very small, and wala tayong makikitang difference between the original length and the projection of its deflected length. So consequently, the elastic curve is very flat and its slope at any point is very small. That's why the slope can now be expressed as our tangent theta is equal to dy all over dx. With a small error, kasi nga the slope at any point is very small, we can set tangent theta is equal to dy over dx be equal to our theta is equal to dy all over dx. So differentiating this equation, we now have d theta all over dx is equal to the second derivative of y with respect to our x. So we can also consider the variation in theta using the ds, or the differential length ds. So this is the differential length ds from our elastic curve caused by bending in the beam. So we have our differential length ds is equal to our rho multiplied by our d theta, tama? So we have rho multiplied by our d theta. We can express that as 1 all over rho is equal to d theta all over our differential length. And since the curve is very flat, we can assume that our differential length s is equal to our dx. We have now obtained this equation, on which our 1 all over rho is equal to d theta all over our differential x, or 1 all over theta is equal to, so this equation is just the same as this one. So the second derivative of y with respect to our x. So we have obtained in chapter 5 the flexure formula, on which 1 all over rho is equal to our moment all over the modulus of elasticity multiplied by our moment of inertia. So we have our moment is now equal to EI all over rho, on which we can also express that as EI multiplied by the second derivative of y with respect to our x. Kasi yung 1 all over rho natin, right, is equal to this one. So, sinubstitute ko lang. Therefore, we now obtained the differential equation of the elastic curve of the beam. So, it is equal to the modulus of elasticity multiplied by the moment of inertia multiplied by the second derivative of y with respect to our x. So this is now the differential equation of the elastic curve of the beam. So again, EI, or the product of EI, is also known as the flexural rigidity of the beam, and it is usually constant along the entire length. So the value of EI depends on the material of the beam. So assuming that our EI is constant, we can now obtain the slope equation specifying the slope or the value of our dy all over dx at any point. So we have the integration of moment plus C1. So this is now our slope equation. Note that our moment here represents the moment equation expressed in terms of x, and our C1 is a constant to be evaluated from the given conditions of the loading. So integrating again this equation, we now obtain the required deflection equation of the elastic curve. So, integrate pa natin to ulit. So, we have EI multiplied by y is equal to So, this is now our deflection equation. So, this is our deflection equation. So this deflection equation of the elastic curve specifies the value of y for any value of x, or madedetermine natin yung deflection ng beam at a certain distance x. So C2 is another constant of integration that must be evaluated from the given conditions of the beam and its loading. So, hindi porket nakarinig na kayo ng integration is matatakot na kayo. Actually, this is easy. This is just a piece of cake from the other methods. So, we have now here our procedure, or summary of the procedure for the double integration before we go to our examples. Step number 1 is to sketch the elastic curve of the beam, taking into account the boundary conditions. So, kindly take note of these conditions. Zero displacement at pin supports, as well as zero displacement and zero slope at built-in supports. So, meaning, y is equal to 0 at pin supports as well as in built-in supports. So, on the last chapter that I have discussed, chapter 5, tinuro ko na sa inyo on how to sketch the elastic curve of the beam. So first is to draw, of course, the moment diagram, but it can now be made easier if you take into account these boundary conditions. So always consider this zero displacement at pin supports and zero displacement and zero slope at built-in supports. Step number 2, use the method of sections to determine the bending moment at an arbitrary distance x from the origin. always show moment acting in the positive direction on the free body diagram. If the loading has discontinuities, a separate expression for moment must be obtained for each segment between the discontinuities. Also, on chapter 4, we already tackled method of sections to determine the bending moment M. By integration, the expressions for moment twice, obtain an expression for EI dy all over dx in each segment. Do not forget to include the constants for integration. So the constants are the C1 and C2 and so on. And the fourth one is to evaluate the constants of integration from the boundary integration and the continuity integration on slope and deflection between segments. So let us do our examples for double integration. For example number 1, a concentrated load of 300 Newton is supported as shown. Determine the equations of the elastic curve between each change of load point and the maximum deflection of the beam. So our first step here is to first get the value of the reaction 1 and reaction 2, or the supports. So by taking the summation of moment at R2 is equal to 0, so we have R1 multiplied by 3 meters, then minus 300 Newton multiplied by 1 is equal to 0. Therefore, R1 is equal to 100 Newton. And then taking the summation of forces vertical is equal to 0. So we have 100 plus R2 minus 300 is equal to 0. Therefore, we have 200 Newton. So this is 100 Newton and this is 200. So dito sa problem na to, it is already indicated yung elastic curve. Nakalagay na dito yung elastic curve. So paano natin nakuha tong elastic curve? By drawing the moment diagram, makukuha nyo or makikita nyo doon kung paano yung elastic curve. Or simply to say, if you take into consideration yung mga important notations natin at the last slide, which is this one, the boundary conditions with zero displacement at pinpoints. Kaya kung makapansin nyo, there is zero displacement at these supports in R1 and in R2. So let us proceed. So let us have a section here. Yan. Let's say we have section AA here para makuha natin yung moment dyan sa part na yan. So drawing natin dito. So this is 100 Newton. This is 300. So this would be our distance x. This is 2 meters and this is x minus 2. And we know that our moment is equal to the modulus of elasticity multiplied by the moment of inertia multiplied by the second derivative of y with respect to our x, in which is equal to, so 100 multiplied by x minus 300, we have x minus 2 yung moment arm, x minus 2, and this is in Newton that meter. So ito na yung ating moment equation. And then taking the integral of the moment, makukuha natin yung slope equation. So integrate natin to. So we have EI dy all over dx. Integrate natin tong equation na to. So we have 100 x squared all over 2 minus 300 x minus 2 squared all over 2 plus the constant, and that is Newton dot meter squared. Simplify lang natin. So we have 50 x squared minus 150 x minus 2 squared plus C1. So ito na yung ating slope equation. And then, integrating again this equation, makukuha natin yung deflection equation. So, we have EIY is equal to 50x raised to 3 all over 3 minus 150 of x minus 2 raised to 3 all over 3 plus C1x plus C2 Newton dot meter cube. Then simplifying it further, we have 50 all over 3 x raised to 3 minus 50 x minus 2 raised to 3 plus C1x plus C2. So, ito na yung ating deflection equation. Pero, mabubuo lang itong deflection equation natin and this loop equation if we are able to define or get the value of the constants C1 and our C2. So, by looking at the elastic curve itself, at x is equal to 0, yung deflection is equal to 0. So, substitute natin yan in this equation. So, we have equation 1, equation 2, and equation 3. So, substitute natin yan sa equation 3. Therefore, kung mapapansin niyo dito at this part, substitute lang natin yung value ng x and value ng y into 0. So, it is equal to EI y. So, magiging 0 yan at this part. And then, 0. And then, this one. Take note na kung negative na yung ilalabas nung nasa loob ng ating bracket, considered it cancelled. So, again, kung negative na yung nasa loob ng bracket na to, ika-cancel out nyo na. So, kung sasubstitute nyo yung 0 at this part, lalabas ang negative 2, di ba? So, since it is negative, ika-cancel nyo yun dun sa part na yun. So, cancel that one. And then, substitute natin this one 0. Therefore, our C2 is 0. The value of the constant 2 would be equal to 0. Next, at x is equal to 3 meters, y is also 0. Tama? The deflection is 0 at this part. So, by using equation 2, equation 3 again. So, by using equation 3, substitute na this part. So, we have 0 is equal to 50 all over 3, 3 raised to 3, minus 50, 3 minus 2 raised to 3, plus C1 multiplied by 3. C2 is 0, by the way. So, C1 would now be equal to So, our C1 is equal to negative 133.33. So, negative 133.33. The problem is asking for the equation of the elastic curve. So, for equation 2, we have dy all over dx of 50 x squared minus 150 of x minus 2 squared minus 133.33 Newton dot meter squared. So, ito na yung ating equation for the slope. So, this is the slope equation. And then, for our deflection equation, so we have EI y is equal to 50 all over 3 x raised to 3 minus 50 of x minus 2 raised to 3 minus 133.33 x Newton dot meter cube. So, ito na yung ating deflection equation. Yan. So, ito yung answer natin for the equation. So, we have here 1, 2, and 3. So, next is to determine the maximum deflection of the beam. So, assume natin that the maximum deflection of the beam will occur between these points. between point A and B in which x is equal to 2 meters. So, assume natin na dito sa section na to, mangyayari ang maximum deflection. So, kung maximum deflection natin, this slope or the dy all over dx is equal to 0. So, at dy all over dx or the slope is equal to 0, what is the distance from the left support? So, by using equation 2, so we have here 0 is equal to 50 x squared minus, so kung i-assume natin na nasa loob siya ng distance between A and B which is 2 meters, magiging 0 to. So, let us cancel it out, making it minus 133.33. Therefore, our x is equal to x is equal to 1.63 meters. So, our assumption na yung maximum deflection natin will occur between A and B is correct. Therefore, substituting it using equation number 3. So, substitute na lang yung x using equation 3. So, we have EI y is equal to 50 all over 3, 1.63 raised to 3. So, canceling this portion kasi nga magiging negative na. So, keep that in mind. Na kung negative na, yung nasa loob ng bracket, cancel it out. So, minus 133.33 multiplied by 1.63. So, our EIY would now be equal to So, it is equal to negative 145.15 Newton dot meter cube. So, kung may value yung ating EI or yung flexural rigidity natin, madedetermine talaga natin yung exact amount ng ating Y. So, kung makapansin nyo, yung ating unit is in Newton dot meter cube kasi nga wala tayong value ng EI. So, kung sinabi sa problem or kung ni-specify sa problem yung value ng ating E tsaka I, makakuha tayo ng deflection or deflection ng unit is naka-meter. So, this would be our final answer. So, this one for the maximum deflection in the beam. And also, this negative sign indicates that Y is downward or yung deflection natin is in downward motion. For problem number 2, find the value of EIY at the position midway between the supports and at the overhanging end of the beam shown. So, also, the problem now indicated yung shape ng ating elastic curve. Yan, nilagay na dito sa problem. So, to save time, nilagay ko na dito yung shape ng ating elastic curve. So, first step again is to determine the values of the reactions. So, we have here reaction to to. So, we have summation of moment at R2 is equal to 0. So, we have R1 multiplied by 6 meters minus 400 of 3 and then 1.5. This is 1.5 plus 2 plus 600 of 2 is equal to 0. Therefore, reaction 1 would be equal to 500 Newton. And then, taking the summation of forces vertical is equal to 0. So, we have 500 plus R2 minus 400 multiplied by 3 minus 600 is equal to 0. Therefore, R2 now is equal to 1,300 Newton. Yan, meron na tayong values ng R1 and our R2. The next step is to place a cutting section between, so let's say this is A, B, C, D, and E. So, between D and E, we have here cutting section. So, isolate ko lang. So, we have here 500 Newton. This is 400 Newton per meter. We have here 1,300. And this is our A. So we have here 1 meter. So this would be the distances. So 1 meter, 3 meters, 2 meters, and the whole of this is x, diba? So we have x minus 6. So ang approach na gagawin natin dito sa uniform distributed load is to draw an imaginary loading up to the cutting plane. Ang imaginary loading ng value din niya is 400 Newton or 400 Newton per meter. And to balance that one, syempre maglalagay rin tayo dito, which is also equal to 400 Newton per meter. We are now ready to determine the moment equation. So we have moment is equal to EI of the second derivative of y with respect to x. So we have here 500 multiplied by x minus 400 of x minus 1. Moment arm is x minus 1 all over 2 plus 400 of x minus 4. Moment arm is x minus 4 all over 2 plus 1,300. Moment arm is x minus 6. So simplifying this further, we have 500x minus 200 of x minus 1 squared plus 200 of x minus 4 squared plus 1,300 of x minus 6. Yan. So this is now our moment equation. So integrating it once again, makukuha natin yung ating slope equation. So we have 500 x squared all over 2 minus 200 x minus 1 raised to 3 all over 3 plus 200 of x minus 4 raised to 3 all over 3, tama, plus 1,300 of x minus 6 squared all over 2 plus our constant 1. So simplifying it further, we have here 250 x squared minus 200 all over 3 of x minus 1 raised to 3 plus 200 all over 3. So mas maganda na i-retain na lang yung fraction form para exact yung makukuha nating mga values, comparing it kung i-decimal point pa natin. So we have plus 650 of x minus 6 squared plus c1. So I forgot to put the unit, so we have Newton dot meter squared. So this is Newton dot meter. Integrating this equation once again, makukuha natin yung ating deflection equation. So we have here 250 so we have 250 x raised to 3 all over 3 minus 200 of 3 x minus 1 raised to 4 all over 4 plus 200 all over 3 of x minus 4 raised to 4 all over 4 plus 650 plus 650 of x minus 6 raised to 3 all over 3 plus c1x plus our constant 2. So simplify pa natin. So we have here e1 or eiy is equal to 250 all over 3 x raised to 3 minus 50 all over 3 x minus 1 raised to 4 plus 50 all over 3 of x minus 4 raised to 4 plus 650 of x minus 6 raised to 3 all over 3 plus C1x plus C2 Newton dot meter cube. So next step is to determine the value of our constants C1 and C2. So at x is equal to 0, y is equal to 0. Therefore, C2 is also equal to 0. And then at x is equal to 6 meters, y is also 0. So using the deflection equation, so we have 0 is equal to 250 all over 3, 6 raised to 3, minus 50 all over 3, 6 minus 1 raised to 4, plus 50 all over 3 of x minus 4 raised to 4. So 0 na dito sa part na to, plus C1 multiplied by 6. Therefore, our C1 is equal to negative 1,308.33. Yan. So, kompleto na yung ating deflection equation. So, we have here EIY is equal to 250 all over 3 x raised to 3 minus 50 all over 3 of x minus 1 raised to 4 plus 50 all over 3 of x minus 4 raised to 4 plus 650 all over 3 x minus 6 raised to 3 minus 1,308.33 x. We are now ready to determine the value of EIY at the position midway between the supports and at the overhanging end of the beam show. So at the position midway, at x is equal to 3 meters, so ito yung supports, which is 6 meters, so the mid span is at the 30 meters. So we have x is equal to 3 meters. What would be the value of our EIY? So EIY is equal to, substitute na lang, so 250 all over 3 raised to 3 minus 50 all over 3 of 3 minus 1 raised to 4. At this part, cancel out kasi negative na. And also at this part, cancel out kasi negative. So we have minus 100 or 1,308.33 multiplied by 3. Therefore, our EIY is equal to negative 1,941 Newton dot meter cube. So ito yung answer natin between the supports. Next, at x is equal to 7 meters or no, 8 meters because it is asking at the overhanging end. So at x is equal to 8 meters, what will be the value of EIY? So same, substitute na lang 8 dito. So 250 all over 3. So we have 250 all over 3. 8 raised to 3 minus 50 all over 3. 8 minus 1. 8 minus 1 plus 50 all over 3 of 8 minus 4 raised to 4 plus 650 all over 3 of 8 minus 6 raised to 3 minus 1,308.33 multiplied by 8. Therefore, EIY is equal to negative 1,816.64 Newton dot meter cube. So this would be now our answer for the value of EIY at the overhanging end. So this is for the midway. Next, a simply supported beam carries the triangularly distributed load as shown. Determine the deflection equation and the magnitude of the maximum deflection. So, again, our first step is to determine the value of R1 and our R2. So, by taking the summation of moment at R2 is equal to 0. So, we have R1 multiplied by L minus, we have here 1/2. So, itong area muna to, 1/2 W multiplied by L all over 2. Moment arm is 1/3 of L all over 2 plus L all over 2. Next triangle, minus 1/2 of W multiplied by L all over 2. Moment arm is 2/3 of L all over 2. Is equal to 0. Therefore, so simplify natin yan. So we have R1L minus, have 1/4 Therefore, R1 is equal to WOL all over 4. So, since it is symmetrical, obviously R1 is equal to R2, tama? So, we have R2 is equal also to WL all over 4. So, this is WOL all over 4. Same with this one. Next is to pass section here. So, since it is symmetrical, assume natin na the deflection is also symmetrical. Or, obviously, the deflection is symmetrical since the loading is also symmetrical. So, by cutting at that section, so we have here so this would be Y and this would be our X. So by ratio and proportion, we have WO of L all over 2 is equal to Y all over X. Therefore, our Y is equal to 2 of WOX all over L. Yan. So, pwede natin kunin yung ating moment equation. So, we have here EY of D squared or the second derivative of Y with respect to X. So, we have WL all over 4. Moment arm is X minus 1/2 of 2WL or WOX all over L multiplied by X multiplied by X 1/3 of X. So simplifying it further, we have here WL all over 4 X minus WOX raised to 3. Tama. We have 3L. We have 3L. Yeah. And then, next is we have here our slope equation. So, dy all over dx. We have WL all over 4. X squared all over 2. simplify pa natin. So we have here W L x squared all over 8 minus W of 12L x raised to 4 plus C1. So integrating it once again, makukuha natin yung ating deflection equation. So we have EIY. EIY is equal to ayan. So, meron tayong deflection equation and we are now ready to determine the value of constant 1 and constant 2. So, at x is equal to 0, y is also equal to 0. Therefore, C2 is equal to 0. So, not all the time, C2 is equal to 0. Kindly take note of that. Next, due to the symmetry, we know that the deflection will occur at the midspan, in which the slope would be equal to 0. So, at x is equal to L all over 2, the slope would be equal to 0, in which our maximum deflection will occur. So, we have, using this equation, so we have 0 is equal to WO L all over 8 L all over 2 squared minus WO and then 12L L all over 2 raised to 4 plus C1. Therefore, our C1 is equal to raised to 3 and then 192 minus, so simplifying it further, our constant 1 would now be equal to negative 5 all over 192 of W L raised to 3. Yeah. So this is now our value for C1. And we are now ready to determine the deflection equation and the magnitude of the maximum deflection. Therefore, our deflection equation now would be equal to WOL over 24 x raised to 3 minus have 60L x raised to 5 minus 5 all over 192 of WOL raised to 3 multiplied with x. So, ito na yung ating deflection equation. Next is to determine the magnitude of the maximum deflection. So, at x, we know that at x is equal to L all over 2. Doon magkakaroon yung maximum deflection. So, doon mag-a-occur ang maximum deflection. Therefore, substitute nyo lang. We have here, wala pala tayong value ng flexural rigidity. So, it is in terms of EI pa din. So, we have W o L all over 24 L all over 2 x raised to 3 raised to 3 minus WO 60L L all over 2 raised to 5 minus 5 all over 192 L raised to 3 of L all over 2. Yan. Therefore, so simplified equation would be equal to negative WO L raised to 4 all over 120. So, this is now our maximum deflection that will occur on the midspan.